All right, we're recording. Thanks a bunch, James. Get us going.
All right. Welcome back. We are excited to welcome Dr. Joshua Krissansen-Totton. Joshua is an assistant professor in the Department of Earth and Space Sciences at the University of Washington. He earned his PhD in Earth and Space Sciences and Astrobiology at UW and was a NASA Sagan Fellow at UC Santa Cruz before joining the UW faculty. His research explores the atmospheric and geochemical evolution of rocky planets with the goal of understanding planetary habitability and identifying potential biosignatures in exoplanet atmospheres. He develops models that connect planetary interiors, surfaces, and atmospheres over geological timescales to explore the coevolution of life and the environment. Thanks for being here with us today. The floor is yours.
Thank you again, and thanks for your patience, everyone. Yes, as you heard, I think of myself primarily as a planetary scientist interested in the search for life, but a lot of my PhD work was focused on Earth's carbon cycle, the role of seafloor weathering, reverse weathering, and so I thought I'd revisit that today with hopefully some interesting updates from the literature in the last few years. And I can't see anyone or anything, so please, interrupt if there are any issues or if you have any questions as we go. So just to start things off, this is kind of the textbook view of how Earth's carbon cycle maintains Earth's habitability. CO2 is degassed into Earth's atmosphere ocean system from the interior and then removed from the surface via weathering and the subsequent deposition of carbonate rocks. Just realized you can't. Can you see my cursor, or is that not working?
We can see it. It's just very small.
Okay. Try not to use it too much. And so, the premise here is that the carbon removal part of the process, the weathering removal, is temperature dependent. So if you have some external perturbation, or if, say, the brightness of the sun is increasing over time, then this is going to warm the surface, increasing the rate of weathering, increasing that drawdown of CO2. So CO2 in the atmosphere goes down. This cools the climate until you're restored at a new steady state where weathering balances outgassing, but CO2 is lower. So this is the thermostat in a nutshell. And we can think of weathering as a two-step process where initially you're dissolving CO2 in rainwater to dissolve rock, release cations that then ultimately make their way into the ocean, where they form carbonates, removing the carbon from the system. And it is this dissolution of silicates on land part that is generally thought to be temperature dependent. This is just another depiction of the same thing. And as has been argued for several decades now, at some level, a thermostat must operate to ensure that weathering and outgassing balance. If you do not have weathering, balancing, outgassing, then relatively quickly on geologic timescales, you either have a huge buildup of CO2 or you remove all your CO2 from your atmosphere. Now, as I previously alluded to, we generally think of this weathering thermostat as happening on the continents, but there is a similar set of processes happening in the seafloor, in oceanic crust, where seawater percolating through the crust can dissolve surrounding rock, releasing cations that then precipitate carbonate in the pore space. So you can get these veins of carbonate through as a consequence of circulation of seawater through oceanic crust. And so this is, naturally we don't see the evidence of this so obviously as we do carbonates deposit on shelves, because typically when you form carbonate in oceanic crust, it then gets subducted. But in rare instances where the rock does not get subducted, you do see this. So these are some pictures from the Troodos ophiolite in Cyprus at an AGU meeting a few years ago. And you can tell that I'm a theorist and a terrible field geologist because I didn't think to put a hammer or anything else for scale, but these rocks are just full of carbonates from the alteration that's happening in the first few hundred meters of pillow basalts. So this does operate on the Earth today, but we can think about planets such as the early Earth, where there was perhaps less land, faster spreading rates, more CO2 in the atmosphere, and so perhaps this seafloor weathering played a larger role. Okay, so with that as introduction, this is what I wanted to cover today. This is a three-part talk. So in part one, I'll talk about how the carbon cycle has potentially regulated Earth's climate through time and the role of seafloor weathering. Part two, I'll talk about how reverse weathering could change the story of Earth's climate evolution. And time permitting, in part three, I'll say a little bit about some recent work I've been doing on how exoplanet observations could improve our understanding of planetary climate regulation. Okay, so part one. So this is going back to some of my PhD work and attempts to quantify the dependencies of seafloor weathering and how it is affected by ocean conditions, ocean pH, temperature, and so on. So you can, of course, do experiments where you try and measure the pH dependence of the dissolution reactions that are important. There's a number of ways you can get at the temperature dependence of seafloor weathering. You can, of course, also do experiments, but there's also really interesting data going back the last 100 million years or so, where you can infer a temperature dependence of seafloor weathering from observed changes in bottom water temperature, the corresponding changes in carbon content of oceanic crust, and various other isotopic proxies. By fitting that, you can infer a temperature dependence. But to get to the thermostat aspect of this process, you need some way to connect the surface temperature, which is controlled by atmospheric CO2, to the temperature of water circulating through oceanic crust. And so sort of attempted to define a relationship here based on 3D models of ocean circulation that can relate deep ocean temperature to surface temperature. And it turns out to be a shockingly linear relationship. And so if you put all that together in a carbon cycle model, you can attempt to investigate how seafloor weathering has affected climate evolution. So this is what we did. This is a very simple model of the carbon cycle, tracking fluxes of carbon and fluxes of alkalinity in and out of the atmosphere-ocean system, as well as in and out of the pore space of oceanic crust. And I just put these equations up here to show that there's really no magic here. It's a very simple system of equations, just tracking those fluxes of carbon alkalinity and exchange between the ocean and the pore space. And so everything I just talked about on the dependencies of seafloor weathering is all embedded in this term here, the dissolution of oceanic crust, a contributor or a source of alkalinity in the ocean pore space. So this was kind of the first application of that model, starting just with the last 100 million years of Earth history, a time span over which there's a reasonable amount of data. And so what we did here was sort of a fit where we said, we don't know a lot of things about how the carbon cycle works. We don't know, the temperature dependence of weathering, perhaps. We don't know long-term climate sensitivity and various other forcings. So we allowed those to vary freely and then demanded that the evolution over the last 100 million years fit these proxies. So it has to recover the decline in CO2 since the mid-Cretaceous, increasing ocean pH, change in carbonate saturation state, and changes in climate and deep ocean temperature. And so when you do all that, and you you fit to these various proxies, you get out some constraints on how the carbon cycle seems to work. And I'll just briefly mention, I'm only going to really talk about one of these in detail, but just to mention them all briefly. So these gray distributions are the constraints that you get out on various carbon cycle parameters based on that fit. And so we find that the long-term climate sensitivity, as the warming you get in response to a doubling of CO2, is quite large on these long geologic timescales. And this is consistent with a lot of other paleoclimate work. We also found, consistent with previous work, that there has to be something other than the CO2 temperature feedback driving changes in weathering over the last 100 million years. And we're able to constrain the magnitude of that. But crucially, we also constrained this temperature dependence of continental weathering. So this is a little bit confusing, so let me just take a minute to explain it. On the right here is the nominal equation we use for the continental weathering flux, and you can see it depends on the change in surface temperature. It's exponential of the change in surface temperature divided by this e-folding temperature, TE. And so that defines the sensitivity of weathering to temperature. When that TE number is large, you need a large change in surface temperature for a given to achieve a given change in weathering. And so a large value for that e-folding temperature means a weak thermostat, a weak response of weathering to changes in temperature. And so as this figure shows, we found that in order to fit the data for the last 100 million years, you need a fairly weak thermostat. If you don't have that, you can't explain the fairly large change in surface temperature since the mid-Cretaceous. And as the red arrow indicates, typically carbon cycle models do assume a much more effective thermostat, a much stronger response of weathering to temperature. And since we published this, there have been a number of follow-up studies that have come to somewhat similar conclusions. There's this Herbert paper from a few years ago that also was a fit to proxies, in this case just over the last 20 million years, but also found the need for a fairly weak thermostat. This Brantley paper was looking at the temperature dependence of weathering on different spatial scales, and found that while, on the scale of watersheds, so I should say the y-axis here is kind of a measure of the strength of that temperature response of weathering. And while there is a strong temperature dependence on the scale of watersheds, when you do an inventory of all of the whole planet and sort of carefully think about how much of the surface is runoff limited versus kinetically limited, you find that the global response of weathering to changes in temperature is quite weak. Preceding all of this was this Marin Chamberlain modeling paper that was applied reaction transport models to weathering, and the take home here is similar, that for the global average, the response in the weathering flux to a given change of temperature is fairly modest. And there have been some other papers too. This Coogan and Dosso paper is also a fit over the last 60 million years to various isotopic proxies, allowing the temperature dependence of continental and seafloor weathering to be free parameters, and also found a very weak continental thermostat. So if you put all that together, so this is the figure I showed you before with our gray distribution being our result or our constraint on the temperature dependence of continental weathering, and then I've overplotted, tried to overplot on the same scale these various other papers that have come to similar conclusions. And as you can see, they're broadly consistent in that they're pointing in the direction of a weak continental weathering thermostat. So we'll come back to the implications of this in a moment. What I wanted to talk about next was if we take this carbon cycle model and apply it to all of Earth history, what does this show? And so this is also some work that I did during my PhD, The approach here was to try and be as agnostic as possible on the various things we don't know about the Precambrian Earth. So how has land fraction evolved? How has heat flow from the interior evolved? How has biology affected weathering? So we sort of adopt the gray shaded regions here. Hopefully you can see that. Sometimes it comes out faint, but we adopted these broad ranges as kind of inputs into the carbon cycle evolution. And this is what you get. This is time on the x-axis going back. Sorry that the time axis is reversed, but from 0 to 4 billion years ago, showing time evolution at ocean pH, CO2, outgassing, temperature, and the continental and seafloor weathering fluxes. And the gray shaded region is just the huge uncertainty envelope from all these uncertain input parameters. But unsurprisingly, you get CO2 drawdown as the sun is getting brighter over geologic time. And the combination of continental and seafloor weathering just keep surface temperatures relatively temperate, albeit with very large uncertainties. Okay, so in this paper, we kind of asked the question: can you break this? What extreme things could you do that would cause the early Earth to not be temperate? And so you can do things like take away all the land in the Archean and let the seafloor keep surfaces, maintain surface temperature. Likewise, you can take away the seafloor and see what happens. Things do start to get a bit warm here. It's a point we'll come back to. And you can also do things like add a lot of methane into the Archean atmosphere and see how that affects the carbon cycle evolution. But broadly speaking, the overall picture does not change. So since this was published a while ago now, there have been a number of interesting follow-ups to this. One recent one from earlier this year, the Squad and Koranaga paper, is a similar kind of investigation looking at carbon cycle evolution over all of Earth history, but rather than kind of sample a very broad range of outgassing histories, this paper includes an explicit model of crustal production and recycling. And so, as you can see here and there, time evolution plots, you have very high net crustal growth early on, or high crustal generation early on, that then tapers off, and that is assumed in order to fit mantle potential temperature and the formation age distribution. But if you use that as an input, then you do get a somewhat different CO2 and temperature evolution, and that you very rapidly remove CO2 from the atmosphere due to that high crustal production early on, and you very rapidly cool off the Earth to very temperate climates. So it's an interesting exploration. The extent to which you believe this kind of depends on the extent to which you believe that that model of Earth's interior evolution. If I take those figures and overplot them on top of the nominal model I showed you earlier, you can see it is sort of skirting the lower bounds of our confidence intervals on Earth's climate evolution, but it does tell a somewhat different story about what Archean climate would be like. Something else that we explored subsequently to these earlier, this first study was looking at the effects of impact ejecta on the very early climate. If you have a very high rate of material bombarding the Earth's surface, you create a lot of weatherable ejecta that can draw down CO2. As you can imagine, a lot of uncertainties here, but it does seem to suggest, when you paste that onto the end of the evolution here, the possibility of a very cool Hadean climate. But as I said, the uncertainties are quite large. Okay, so that's kind of an aside. I wanted to return to this this figure that I showed earlier, perhaps suggesting a weak continental weathering feedback. So what happens if we take this seriously? In the previous model runs I showed you, it doesn't explicitly assume this weak dependence. But if we allow, or if we insist that continental weathering is a weak feedback, and put that into our whole Earth all-time carbon cycle evolution, and for the sake of a null hypothesis, let's just ignore seafloor weathering for now, just have that weak continental weathering thermostat, and additionally assume that the amount of land in the Archean was fairly low. And there's some interesting recent work suggesting that that might be the case. So if you make those assumptions, you start to get a climate evolution that is looking less likely, right? So you can see here the temperature evolution on the bottom left in the absence of seafloor weathering, and if you assume a very weak continental weathering thermostat, you start to get temperatures that are unphysical, that are far too high for the Archean Earth, and certainly inconsistent with evidence of glaciation in the Archean. And so it seems like this doesn't really work, right? The continental weathering alone, if it's a weak thermostat, can't maintain a temperate climate for all of Earth history. And there was this interesting paper out earlier this year by Brandon Coy that came to the same conclusion, but through a very different method. So in this paper, they set up kind of an idealized model of motion of continents on geologic time and how that affects weathering rates. So they have these disks representing different continents that just sort of randomly walk across the Earth and occasionally collide. And when they collide, there's uplift, you create freshly weatherable material. But if they haven't collided for a while, you don't have as much material to weather. And so when you just run that model forward in time, this is one example of that, showing the evolution of atmospheric CO2 through time, as well as the collision area. And so as you'd expect, you get a kind of random walk in CO2, but every so often you get a situation where, continents haven't collided for a while and CO2 starts to increase excessively, or the opposite, where you have a lot of collisions and you throw your planet into a hard snowball. So using this model, they can, of course, run many model realizations. This is time, again, on the x-axis going forward in millions of years. You can see, so the green model runs are the ones that survive. So there's this gradual CO2 drawdown over planetary history. And that's, in this particular case, 32% of the model runs. But you also get a whole bunch of model runs that don't survive, that either go into a hard snowball, or there is sort of catastrophic CO2 accumulation and a very large increase in surface temperature that, I mean, maybe you would recover from it, but it would certainly be pretty limiting for complex life. And so what this suggests that there's this element of randomness to the thermostat, that our survival is not guaranteed, and you can do these plots showing how likely is your planet to survive as a function of the amount of land and the number of disks or the number of continents. And while Earth is sort of somewhere up here in the high survival rate today, certainly on the early Earth, it was not. And so you might wonder, is it luck that led us for Earth to have maintained its habitability? But crucially, everything in these simulations on the left ignores seafloor weathering. And if you put seafloor weathering back into the model using a parameterization similar to what I've been using in our models, there are no longer any catastrophic warming model runs. Basically every model run survives because the additional thermostat provided by the seafloor safely buffers climate against the random variation caused by how frequent continents are colliding to create increases in weathering on land. So based on all of that, I guess I would argue that I think there's there's evidence that continental weathering alone can account for Earth's climate stability, and that seafloor weathering may have had an important role, particularly on the early Earth. So I realize I am running out of time, and I'm only on part 2, but I'll try and get through the rest of this and leave some time for questions at the end.
I wouldn't worry too much about time, Josh, since we slowed you down so much. But if
Sure,
you
but
have an issue, go for it.
I mean, I know people may need to go on the hour, so so next I want to talk about how reverse weathering could change the story that I've just showed you of Earth's climate evolution. Going back to our sort of textbook schematic of the carbon cycle, something that's often not really discussed in these sort of introductory treatments is what exactly happens to this dissolved silica that gets produced when you weather rocks. On the modern Earth, and by modern I mean most of the Phanerozoic, that dissolved silica is rapidly consumed by biogenic silicifiers, so diatoms, sponges, they remove it. And so dissolved silica concentrations in Earth's oceans today are fairly low. But it has been argued that in the Precambrian oceans, before there was sort of ecologically significant biological silicification, there may have been much higher dissolved silica concentrations in the ocean, perhaps even closer to saturation. And the exact concentrations are, of course, subject to debate, but certainly higher concentrations much higher concentrations of dissolved silica seem plausible. And so there's this possibility that perhaps those higher dissolved silica concentrations drove higher reverse weathering rates in the Precambrian. What do I mean by reverse weathering? So again, going back to our schematic, this two-step process on the right-hand side is generally thought of as forward weathering. But if you have a situation where you've got weathered silicates, so you've got cation poor amorphous aluminum silicates, you've got a lot of cations in solution, you've got a lot of dissolved silica, then the back reaction can occur where you take bicarbonate in solution and you reform CO2, removing that alkalinity from solution. And this is sort of a generic form of that reaction. There are different kinds of reverse weathering reactions we can imagine. Some, in principle, can happen straight from dissolved constituents. We have a cation in solution, dissolved silica, bicarbonate, and you make a cation silicate, and you turn that bicarbonate back into CO2. But you can also do it with the existing cation poor minerals, kaolinite, removing, crucially in all of these reactions, you're removing alkalinity and you're turning bicarbonate back into CO2. And so going back to our schematic here, you can imagine the effect of switching reverse weathering on, going from, say, a modern-like state where there perhaps isn't so much reverse weathering to a situation where the reverse weathering flux is high. Well, to balance the carbon cycle, you're going to need a higher rate of forward weathering to ensure you're still depositing the same amount of CO2 that you're outgassing. And so as a consequence, you need a warmer surface climate that is more CO2 to ensure balance between the carbon cycle. So this was essentially the idea of Isson and Planabsky in this paper from 2018, where they noted that, yes, there's been this there was a much higher dissolved silica concentration in the oceans in the Precambrian due to the lack of biogenic silicification. And so this high dissolved silica concentration could have driven more reverse weathering and as a result produced much higher CO2 levels and warmer climate. So I thought this was a really interesting idea. I was skeptical of some of the details in this paper, and specifically, the pH dependence of reverse weathering and imposing silica through time. And so we decided to explore this with the same model that you've seen previously. So this again is a box model of the carbon cycle, same equations that you've seen before, except added to that was keeping track of the dissolved silica sources and sinks in and out of the ocean, which of course includes this reverse weathering term. Now, actually calculating what the reverse weathering flux is through time is challenging. Our approach was to try and do it with a sediment diagenesis model. So keeping for a given sedimentation rate, keeping track of reverse weathering reactions through the sediment column. And the schematic is just showing you how the situation might change, going from the Phanerozoic, the modern, where the dissolved concentrations of silica in the ocean are low, but can increase as you go into sediments, as you dissolve silica that's been deposited, versus the Precambrian, where you have very high dissolved silica concentrations in the ocean, and then they diminish into sediments as reverse weathering reactions removing them. So a lot of unknown parameters here, but we sort of did our best to put together this model and then see how it plays out in sort of deep oceans where there's low sedimentation versus coastal conditions, and then do kind of a weighted average. Okay, so keeping in mind the time, this is the results that you get when you put reverse weathering into the carbon cycle model. And I should say that the solid blue lines and dashed lines are what you saw before. So before we were assuming anything about reverse weathering, and then the black and gray shaded regions are what you get in this nominal model when you put in reverse weathering and you track silica and so on. So this is kind of the bottom left here is kind of the forcing, and that we switch on biological silicification and see how the reverse weathering flux and abiotic silica removal responds. And we're able to do this in a way that kind of broadly recovers these semi-quantitative estimates of the dissolved silica concentration in the ocean through time. And as expected, you do get this large change in the reverse weathering sink. In this particular case, we're assuming that the modern sink is fairly small, and so there's room for this large increase. And consequently, you do get some difference in the CO2 in the climate evolution compared to what we had before. In the blue, you do get elevated CO2, particularly in the Proterozoic and the mid-Proterozoic, which causes about 5 degrees of warming through that time. It diminishes as you go back into the Archean, because we're assuming that sedimentation rates are a strong control on reverse weathering, and if you have less land, presumably you have less sedimentation. But you can also see here how, as I described before, when you go back into the Precambrian reverse weathering, the red must be much higher, and so must forward continental weathering to ensure balance of the carbon cycle. So this is a tidy story, but unfortunately, this doesn't represent the true uncertainty in these processes. This is one particular case for some set of choices about the modern reverse weathering flux and the kinetic dependence of weathering, but you can make other seemingly equally plausible choices in those parameters and get a very different looking carbon cycle evolution. So here we've assumed the kinetic dependencies of reverse weathering weaker. We've assumed a larger modern flux of reverse weathering based on various recent estimates. And in this case, you find that there really isn't much of a change in reverse weathering, even though you're still recovering that huge change in dissolved silica concentrations going from the Precambrian into the Phanerozoic. And so consequently, the effect on CO2 and temperature evolution is pretty negligible. There are also seemingly plausible sets of parameter combinations that give you an excessive amount of warming in the Proterozoic. And this is not realistic, I don't think. This is disagreeing with CO2 proxies in a pretty dramatic way. But this is just to show that there's a lot of uncertainty, specifically in kind of the sediment diagenesis model. So this was a somewhat frustrating result, just basically to find that, this could be really important, but we feel like we don't know the kinetics well enough to be definitive. Probably some additional constraints are going to be necessary. So this is kind of the take home from that when you build a self-consistent carbon and silicon cycle model, it shows that certainly an enhanced reverse weathering flux could have been a substantial contributor to mid-Proterozoic warmth. But the uncertainties in the kinetics are really too large to be definitive. At least they were at the time when we did these calculations. Since then, there have been some interesting ideas using lithium isotopes as a possible tracer of reverse weathering. And I won't describe these studies in the interest of time, but there is, when you look at kind of the evolution of lithium isotopes over all of our history, there is some clues perhaps that there is a change in reverse weathering that could be important. Okay, so it's 10:02, so let me just for a few minutes say something about what we might, what exoplanet observations could potentially teach us about planetary climate regulation. So this is hopefully an application of Precambrian geology that'll be of interest, an astrophysical application, and something I've been working on a lot over the last year or so. So this CO2 evolution that I've been showing over and over again is, of course, a possible solution to the faint young sun problem, and that the silica weathering feedback buffers surface temperatures, higher levels of CO2 when insolation was low. And so taking that logic, you could ask the question, well, what do we predict for rocky exoplanets, assuming that silicate weathering regulates climate elsewhere in the same way it does on Earth? And so, of course, you would predict that as you get further from the star, you would have increasing CO2. This is kind of the qualitative prediction, and this is sort of a sketch of what that might look like, CO2 versus the flux received from your star. And we tried to be a bit more quantitative with this. It's a paper by Owen Lima, where we took the carbon cycle model that you've been looking at and then folded in all the uncertainties and things we don't know about how the carbon cycle works to predict that trend in CO2 versus orbital distance. So this is, in principle, a testable prediction of the carbonate silicate weathering feedback that you could look for on rocky exoplanets. And you might ask, well, what kind of telescope would you need to do that? And this is sort of Habitable Worlds Observatory is intended to be NASA's next flagship mission, the successor to Hubble and James Webb Space Telescope, and soon the Roman Space Telescope. And this picture was from a meeting I attended earlier this summer, which is the whole purpose was to try and define the science and engineering challenges of this telescope and figure out its architecture. So this telescope would be purpose-built to look for life on Earth-like planets around Sun-like stars. It will be the first telescope of its kind to do that. This is a depiction. It won't look like this, but it might look something like this. It's a 6 to 8 meter mirror in space. And I just show this paper that I've been working on as part of there have been community working groups that have been contributing to this telescope and investigating the different science trade-offs. And so we were looking at what are the capabilities the telescope needs to have for light detection. And this is a figure from that paper, and perhaps you've seen versions of this figure before. On the left here, we're showing Earth's atmospheric evolution through time, and this is obviously a very crude oversimplification, but you have to start somewhere. So the premise here is that we want to at least ensure that our telescope could detect life on Earth at different times in its history, and so you can think about what the spectrum of Earth and the modern, the Proterozoic, and the Archean might look like. What would be the biosignature gases that you could see from their absorption features in the spectrum. But in this exploration, we tried to go a little step further and say, okay, suppose you do get a noisy spectrum of in this case, an Archean-like exoplanet. How well can you constrain the atmospheric properties? So doing a fit to that noisy spectrum and figuring out how well you can constrain things like the amount of nitrogen in the atmosphere or water, or a particular interest to us, the amount of CO2. So this is just an example from those simulations looking at an Archean Earth. Don't worry too much about the different shading colors. These are just posteriors for how good you could determine the abundances of these different gases. And certainly for the Archean, where there is a lot of CO2 around, you could detect the CO2. Whether you could detect it well enough to detect these sort of subtle trends that you might expect from the silicate weathering feedback is unclear, but you could certainly know that it was a fairly CO2-rich atmosphere. And I'm just going to skip over this. This is just showing the different cases for Earth through time, how well you can constrain the amount of CO2 and other carbon-bearing gases, both to understand the climate of these planets, but also to look for signs of life, such as through biogenic methane. For CO2, it's interesting. You can basically detect CO2 for Archean levels of CO2, Proterozoic levels of CO2, but Phanerozoic CO2 is likely going to be out of reach. There just isn't enough CO2 in the atmosphere to see a strong enough absorption feature with this particular telescope. Okay, so the take home here is that we can use these types of Earth system models, carbon cycle models, to make quantitative predictions for rocky exoplanets, and telescopes are currently being planned, such as the Habitable Worlds Observatory, that would have the capabilities to start to interrogate these atmospheres and perhaps provide some constraints on how planetary climate regulation works more broadly. So let me just put up my three conclusions, and I think I will leave it there to make sure there's a few minutes for questions. So thank you so much.
Thanks for an excellent talk. Let's open the floor for questions. If you need to head out, just let us know. Let's first have some questions from anybody that does need to leave at 9. If you can stay a little longer, please wait for the others to ask, but let's go. All right. We've got a couple questions in the chat because I don't see any hands up yet. You say there's a lot of evidence for glaciation in the Archean, but the Archean is a long period and there's no evidence for glaciation during the Paleo-Meso-Archean. Any response to that?
Yeah, I mean, it's a good point. So the main evidence referring to there is this DeWitt fairly near equatorial glaciation. And so I suppose the argument here is that if you had sort of average temperatures that were in the extreme of that distribution, you're getting up to well above 350 Kelvin here, then it's hard to imagine a process that would cause a sudden excursion to such a dramatically different climate with glaciation near the equator and back to that very warm background. But yeah, it is a good point that those episodes of glaciation don't necessarily rule out a warmer average climate for the Archean.
If I can reply to that, Joshua,
Yeah.
the so-called glacial deposits that Martin de Wit and his colleagues describe, they're not glacial deposits. They're normal sedimentary deposits. They were wrong in their interpretation.
Okay, well, thank you. Yeah. So I'm obviously not an expert in these constraints, so yeah, thank you for.
That's my stamping ground, so.
Sure.
Okay.
Yeah.
But
I mean,
thank you for an interesting talk anyway.
Thank you. Yeah. I mean, I think in general, I find the weight of evidence against a very warm Archean convincing based on oxygen isotopes, but yeah, that's interesting to hear about the glacial deposit claims.
All right, I see Greg has a hand up. If you want to unmute and go from.
Yeah, that was great. I've heard these terms, reverse weathering and seafloor weathering, for quite a while now and wondered what they were. And you clarified that really beautifully. I've got a very clear idea of what they are. But I wonder, should either of them be called weathering of any sort? When you say reverse weathering, what you're saying is not weathering. When you say seafloor weathering, what you're saying is seafloor diagenesis, which of course is a little bit different from terrestrial diagenesis. These terms have different names. Why weathering? I mean, what is weathering so great that you have to put weathering in these terms? It's a semantic problem. Yeah.
Sure. I mean, it's an interesting point. I must say I'm not so familiar with the history of how these terms came to be. I think it's useful from the perspective of just understanding the carbon cycle in these analogous processes to weathering on land in terms of the geochemical outcome, right? Whether it's what it's doing to carbonate, what it is doing to alkalinity. And so it's useful for me conceptually, I think, to think of it as weathering, even if, as you say, like mechanistically, what is happening here is quite different to, the processes on land that we think of as weathering.
It's the exact opposite. You're burying stuff. You're not losing stuff. You're not actually depleting materials. You're not reacting things away, which is what happens in a soil or in weathering. You're actually depositing stuff more or less permanently. So it's a very important sink, but it's not, I think, a mechanism that is comparable with weathering in any fashion.
Well, so
anyway,
yeah.
Enough of my rant.
We could go back and forth on this, but yeah.
Of course. Thank you.
All right, Jingjun.
Yes, very nice talk, Joshua. Two questions, but I will yield to others. So ask one right now. In one of the diagrams, you are showing the fraction of the reverse weathering was increasing from Archean to about 1 GA. And I wonder how you would maintain a saturated or supersaturated silica, dissolved silica in the ocean if you have an increased sink.
You're referring to this like weathering fraction and the other one, I think.
Yeah.
And your question is why silica remains high?
Yeah.
So this is partly a consequence of how you parameterize the abiotic sink of silica and reverse weathering. But essentially what we're doing here is we assume that non-biological silica deposition switches on at a certain level of some fraction of saturation, right? And that's kind of an uncertain parameter, but that is what is causing the silica to plateau. And yeah, the reverse weathering flux responds to that higher concentration, but it doesn't completely deplete the ocean of silica because you're constantly supplying fresh silica from weathering. So it's a source sink balance, and this is the steady state that you reach with a higher rate of reverse weathering, a higher concentration of dissolved silica, but it doesn't deplete the ocean of silica. Hopefully that helps.
Okay. Thank you.
All right, Paul.
I agree that the evidence for glaciation in Barberton is equivocal at best, but I would maintain that the Meso and Paleoarchean sedimentary record is too sparse to say whether or not there were quaternary scale glaciations at that time.
Thank you for that comment.
All right, thank you. Daryl, would you like to go now?
I'd agree with that one, Paul's comments. My comment is more on the role of lid tectonics. Your model seems to be based on subduction-related subaqueous weathering, which is well established from the Phanerozoic and modern examples. If we had lid tectonics, would that drive the same hydrothermal cells that would allow the weathering, or would it shut down much more rapidly?
Sorry, you're asking if, so on the earlier.
If lid tectonics rather than plate tectonics was operative in the Hadean and Archean, would that affect your model significantly?
Yeah, that's an interesting question. That's something I haven't explored. There have been attempts to create, carbon cycle models for stagnant lid regime planets, thinking more about, the exoplanet applications. But I don't, at least I'm not remembering off the top of my head if anyone's gone back and looked at Archean evolution with that stagnant lid regime. I don't think so. My guess is that what those models show is that you can, for a time with a stagnant lid, you can buffer climate in a similar kind of way until your crust gets so full of carbon that you get like essentially the carbon starts coming back up again because you keep piling into the crust and there's nowhere for it to go. So I would suspect that it doesn't change the overall story, that so long as you're producing fresh crust and depositing it near the surface, then weathering can occur and you just bury that crust and regulate climate that way. But that would be an interesting thing to explicitly explore. So yeah, thank you.
Okay, thanks.
All right, we've got 2 additional questions in the chat. Because we're on this page right now, I will ask this one. Is the time axis off? The ages of the glacial deposits and the onset of biogenic silica sink seem to be off by about 500 million years.
Yeah, so you're referring to the fact that biogenic silica jumps up a bit early. So there is some evidence for biogenic silicification earlier, like before it became really ecologically significant. I think what we did here was just impose a ramp to kind of integrate over our ignorance there. But yes, if you argue that really this shouldn't only occur until the Phanerozoic, then it does slightly change your climate evolution story, and you get warmer temperatures later into the Neoproterozoic, which may be more difficult to reconcile with what we know about the Earth's climate evolution. So that's a good point.
Eva, would you like to ask a question?
Ava Stuecken had her hand up.
Yes, yeah, so yeah, so yes, thanks for your talk. Thanks for your talk. So I have to get my video and audio going. So yeah, I was just wondering about this on the slide. You have the CO2 outgassing flux there in the top right. And there was a recent study by Lewis Alcott and others where they argued that actually the outgassing flux may have increased over time because of this buildup of carbonate on continents, and you recycle that carbonate. So I guess what are your thoughts on that? Would that impact your results significantly?
It's going to make the early Earth much colder. Is basically we did do some sensitivity tests with that in the original paper, not including reverse weathering, but just supposing a relatively constant or modest increase in degassing fluxes through time. And yeah, I mean, unavoidably that just implies a much colder climate. It would be interesting to see if you impose that much lower outgassing flux in combination with reverse weathering, can you get a climate evolution story that makes sense and is consistent with proxies? But yeah.
Oh, all right, thanks.
Thank you. Jingjin, would you like to go again?
Yes, sir. Sorry, Joshua. It's me again. I'm intrigued by you showing the paper where the continental collision makes such a differences. And I wonder, is the temperature dependence of the seafloor weathering kind of providing any positive feedback to get rid of the hot house?
Yeah, maybe I went over that too quickly, but by the way, so here it is. And I should clarify, this is not my work at all, but I just thought this was a really interesting exploration. So in these model runs shown here, there's no seafloor weathering at all, which is why you get these runaway warming and runaway cooling scenarios, because you occasionally get into a situation where a continent hasn't collided for a while, or too many continents are colliding. But when you impose temperature-dependent seafloor weathering, basically all of these hard snowballs and catastrophic warming outcomes, they disappear. You only get much more regulated temperature evolution, because so long as you have continuous production of oceanic crust and some temperature dependence to respond to changes in surface climate, then you don't have these extreme variations in surface temperature. Does that answer your question?
Yes, a quick follow-up. How is the parameterization of the temperature dependence on the seafloor weathering was being done? Do we have a good empirical constraint on that?
So I believe this paper used the same parameterization that I used in my the first paper I talked about, the 2017 paper that uses Cenozoic records to show changes in bottom water temperature and changes in oceanic crust carbon content, as well as empirical pH dependencies. So to the extent that you believe those proxies and the extent that they reflect the temperature dependence of seafloor weathering, that's where that comes from. But yeah, as you're, I think, alluding to, there is, of course, a lot of uncertainty in the temperature dependence of seafloor weathering more broadly, and it needs to be modeled more mechanistically, I think.
Thanks.
Yeah, I think the inflection of the strontium seawater isotope curve at the Eocene-Oligocene boundary is a very strong indicator that there is a strong temperature dependence of seafloor weathering. Because as the seawater got colder, the seafloor weathering went down, so the continental strontium input became more dominant. And that's in the Coogan and Dosso paper. I think that's
I skipped over this sub-figure here, but I think this is what you're talking about, this change in strontium isotopes.
Exactly, yeah, upper right.
Yeah, reflects the temperature dependence, and you require quite a strong temperature dependence of seafloor weathering to recreate that strontium isotope evolution.
All right, Alex, would you like to ask a question?
Yeah. Thanks, Josh. This was a really big, I think, important topic for our audience. I sort of have a question, not exactly about proxies, but I mean, I know that isotope proxies are developing for tracing reverse weathering, but there's also sort of tracing unusually massive deposits of reverse weathering products. So some iron, like silicate iron formations and ironstones occurred, and I think it can be tempting, from what I can see in the literature, to kind of do an estimate of what the amount of reverse weathering would have been during the deposition of that particular deposit. But to me, when I'm seeing some of this estimation, I have to stop and wonder to myself, like, what if the conditions were uniquely present only for this deposit, and perhaps like volcanic driven, so you uniquely had solutes that wouldn't be there during background weathering and reverse weathering processes. To me, it seems like this makes it not useful to really be trying to quantify the size of these deposits, because they don't really impact background weathering. But I'm curious to hear your thoughts on that.
Yeah, I think it's an interesting point. I mean, I confess I'm not so familiar with the different arguments that have been made for different deposits and what that would imply for fluxes. But when I think it's one of the reasons it's hard, right, is that there isn't just a reverse reaction, there isn't a reverse chemistry. There's just this whole suite of reactions that could be driven by different solute chemistries. And so trying to integrate all of that to get some handle on the global flux through time, and that just feels like a very difficult thing to do. And so I think perhaps for that reason, like the isotopic constraints, tracing, hopefully reflecting sort of broader orthogenic processes could be promising, but yeah, it's a hard problem. I'm kind of stuck, honestly. I sort of produced this paper on reverse weathering. I didn't know like how to do better based on the proxies that we had at the time. So very open to ideas.
Yeah, I really liked the paper. I mean, it was one of those things like throwing all the problems at the wall. But yeah, anyway, thanks for that. Paul?
Well, one of the benefits of reverse weathering is that we need an explanation for the biggest climate anomaly in Earth history, which is the absence of any large ice sheet for 1.5 billion years, from 2250 to 750. We need an explanation for that. And I don't think that's a matter of a lack of sedimentary record.
Yeah, I mean that's certainly part of the motivation for this. Sorry, I keep flicking through slides. I'm never going to find the right one, but that was part of the motivation for that reverse weathering investigation. And it does seem like for plausible assumptions, you do get pretty sustained warmth through the Proterozoic. So I think it could be an important part of the story, but it's just hard to be definitive.
That could even have been held up biology.
Yeah.
If the seawater gets too hot.
All right, we've got one additional question in the chat is what would you say to people who interpret low delta 18O values in the Archean sedimentary archives as evidence of very high temperature in oceans and atmosphere?
I think I will, yeah, I mean, in my mind, if they were extremely high temperatures, there'd be other indicators of it. The weathering proxies, it seems like a simpler explanation is the change in seawater values. But I should just say I'm not an expert in these proxies, so I will pass on that.
Can I come to your rescue on that? I don't think those Archean oxygen values are evidence of high temperatures. They're evidence that the isotopic composition of seawater changed. And that's very clear from work that Ilya Binderman and I have done. Ilya's done a lot more than I have on it. So I think we can rescue you there.
Sure, thank you.
That's a different argument. I'm not basing the idea of high seawater temperature on oxygen isotopes at all. So that's a different question. And I agree with you that seawater oxygen isotope composition has probably changed.
All right.
Thank you. Any other questions? Well, thank you very much for giving this talk. It was wonderful.
Thank you so much for the invitation. Thank you, everyone, for the great questions.
All right, thanks, everyone. Take care. We'll see you next week.
Thanks, Alex.
Thanks, Paul.
Bye.
Thanks again, Josh.
Thanks all.